All right, welcome everyone, and thank you for joining us for OA Week 2023. My name is Kalina Grab, and I am a Canals Fellow in NIWA Ocean Acidification Program and also a GOA-ON Secretariat. So please know that this session is being recorded. OA Week is presented by GOA-ON, and that is the Global Ocean Acidification Observing Network. GOA-ON has three sponsoring organizations. First, NOAA, which is the United States National Oceanic and Atmospheric Administration. Second, IEA-OAICC, the International Atomic Energy Agency, Ocean Acidification International Coordination Center. And third, IOC UNESCO, the Intergovernmental Oceanographic Commission of the United Nations Educational, Scientific, and Cultural Organization. GOA-ON was established in 2012 with just a handful of members, and since then, GOA-ON has grown immensely. It now has over 950 members from over 110 countries. And it also consists of 9 regional hubs which span across continents and oceanographic regions. We'll be hearing from most of them throughout OA Week. If you're not a GOA-ON member yet, you can join GOA-ON by visiting go-on.org. OA Week debuted in 2020 and returned in 2021 when events and conferences were postponed due to COVID-19. Following the successful in-person symposium on the ocean in a high CO2 world in 2022, GOA-ON is bringing around OA research and provide a virtual platform. So we're thrilled to present a wide range of ocean acidification topics and speakers. You're welcome to type any questions into the question box, which can be found at the on your setup. We'll be monitoring incoming questions and we'll pose them to our speakers during the presentation. So for the discussion of your screen, and we'll call on you to ask your question individually. We also will have some polls today that we will participate in as well during this discussion section. So with that, like, as part of the Ocean Atmosphere Interactions Group. She is responsible for Minita Time Series, a long-running transect and multidisciplinary team working on ocean acidification in New Zealand, and she has initiated a coastal ocean series to improve understanding of ocean acidification conditions and consequences for New Zealand coastal ecosystems, communities, and businesses. Kim serves as the IOCCP co-chair and is on the GOA-ON Executive Council. Kim, the floor is yours.
Thanks, Kalina. Hi, everyone. Let me just get myself sorted here. Thanks for joining us for this discussion session on ocean acidification sensors. What's needed and how do we get there? This is this session is a combination of some speakers and then some discussions and polls at the end. Monitoring the state of the ocean, the marine carbon system, is necessary to assess the current status of the carbon chemistry of the coasts and oceans, to assess the rates of uptake of anthropogenic carbon by the ocean, to assess changes in the role of the ocean as mitigation measures are increasingly utilised. That's as countries start to move towards carbon zero by decreasing emissions, and also as active removal methods are started to be explored, including those that directly involve the ocean. And ocean acidification, which we're concerned about, is one of the phenomena associated with the changing marine carbon chemistry. The UN Decade Programme, OARS, Ocean Acidification Research for Sustainability, the aim is to provide systematic evidence of the impacts of the ocean acidification on the sustainability of marine ecosystems, to enhance ocean acidification capacity, increase observations of ocean chemistry changes, and to enhance communication to policymakers and communities, providing the information needed to mitigate and adapt ocean acidification, and to facilitate the development and evaluation of strategies to offset future impacts. OARS fundamentally requires the measurement of ocean chemistry parameters. The OARS program has 5 outcomes, and the ones that are particularly involved with observing and measuring the ocean are outcome number 1, enabling the scientific community to provide ocean acidification data and evidence of known quality, and outcome number 3, co-design and implement observation strategies to ensure outcomes that also require monitoring and observation data. Monitoring the state of change in the state of the ocean acidification, therefore requires, among other methods, suitable sensors to do the job. And in this case, what suitable means is dependent on the environment in which these sensors are deployed, the accuracy and precision that are required by the sensors, and in GOA-ON lingo, we refer to these sometimes as weather quality and climate quality. What type of sensor also depends on the logistics of the deployment, where they're to be deployed, how long they're deployed, and also the resources that are available to the group that are doing the deployment. So today we're going to have various speakers talk about different aspects of this and then have a discussion session afterwards. So very pleased to be able to share with you the perspectives of some different speakers today. We've got Martin, who's from Mexico, who's the co-champion of OARS outcome number 3. We've got Adrian Sutton talking about considerations for choosing fit for purpose ocean carbon sensors. We've got Kalina talking about a handheld spectrophotometric pH analyzer. And then we've got Dwight exploring the benefits and risk of open source application to ocean acidification. So without further ado, we'll get into our speakers. So I'd like to invite Martin to share his screen. I'll just stop sharing mine.
Thank you, Kim.
Martin Hernandez is a specialist in the carbon dioxide system in seawater and marine biochemistry. His research is focused on studying the role of coastal zones in the carbon cycle, including the effects of ocean acidification on marine ecosystems and the relationship of ocean acidification with other stress factors, such as hypoxia, climate change, and CO2 fluxes in coastal regions. Martin has served as the chairman of the Mexican Carbon Program since 2018 and is a member of the North American Carbon Program Science Leadership Group. He's a science member of the Ocean Acidification Observing Network GOA-ON. He's a
Martin, if you just want to take over, I think Kim is having some problems.
Yes, no problem, no problem. Yes, this is the technology at this moment. No, I'm really thanks, Kim, for the presentation, and I'm going to keep. I'm sure she will going back with us. But as she mentioned, well, this morning we have a nice talk related with the OARS by Jan Newton and Steve, related with the Ocean Acidification Research for Sustainability. And I really want to talk with you guys, with all the community, related with the sensors, just the part of the sensors because we will have a lot of challenge related with that. But I so happy that Vero, Veronique Arcon, and myself, as a co-champions, together with the working group, we share with the community this white paper, which is in reality our vision for that we were working in the past 2 years, that we formulated for the future actions related with the activities that we believe that are needed from the ocean community. And then our plan is, this is a part of the bridge, the gaps between the research and the practical application just for the ocean. But you can visit using the code, or you can visit the web page, and you can get this information with more details. I just going to take some brief important consideration that we can use with this session. We want to be sure about for the community that at least 2 CO2 parameters become part of the observing systems. Here, of course, there are all the sensor pH electrodes or spectrophotometric sensor that we can set up in the ocean. There are also, we highlight the developments or the needs for local sensors and to be used in our system, in the coastal, mostly used in the coastal and also where the aquaculture or fisheries activities are needed. And then we can jump to the funders and practitioners, because the funders, like for example, the Ocean Foundation, that we can get some tools for alkalinity and pH. We are learning with the community who have that they are getting a lot of troubles to get the support. And then in our dream, of course, we need this goodwill between the people that use the instruments and also the funders, that we have these gaps of the support to be able to keep the instruments in good shape, to get the money for maintenance, to be in low cost, with the capabilities to be able to set up the instrument and to keep, as I mentioned, in good shape. Of course, with this, the idea is to increase the observations and capability globally, but we are not inventing the wheel. We are using the infrastructure already available. And then we know in the ocean, there are a very good infrastructure already available, but we understand the limitations in the coastal and also with the human is working with aquaculture or fisheries activities. All of this, the idea, as Kim mentioned, the databases need to be reliable to increase the collection, to have in good manners to be ready to share with the community, because with all this information, it will be the support for international policies for a political vision. And really, you can find more about that, about all this white paper with is basically our guide for the vision for the future. But I want to take a few moments really with something that just highlights the Kim about that, because we can separate in the middle, the open ocean, when we have infrastructure already running. We have the coastal zone that we know that we have a lot of challenge there, but also a new elements that we need to consider is which quality and uncertainties we need for the areas with the producers are working on it. They need something as good as the ocean or the coastal zone. It's something that we need to be discussed about that in this document. You can find that. And also will be nice at the end to have some documentation, some feedback from the community. And we know that the climate in the open ocean needs the good of the goods, the best of the goods, to measure the different variables of the CO2 system. We know the academic community is over there, and we know that just a few labs in the world have the best instrument to get the good precision at the good accuracy that the climate requests. Because with this, we can be talking about the long-term anthropogenical driven or multi-decadal timescale information that we needed. We know this is something not for the coastal or for the aquaculture requirement, of course. But we know that in these OARS, we highlight vulnerable areas to be good monitored. Outgoing areas, coastal, of course, coastal areas located in the oxygen minimum zone. And then we are now in the weather quality and the weather precision and accuracy that Kim was talking about. Here are the sensors. The sensors as pH measurements like CFET, CFOX, or spectrophotometric systems like Kim will be talking about, is they can set over there. And you can see that we can be in the precision of 0.02 that is able to offer this information. And we will try to just to help the community. This session is located in the map of the requirements. Okay, with the weather, as we know, is we can follow the short-term variation. We can, of course, to get response for local impacts for the OA dynamics, and we know more about that. But of course, when we're talking about sensors, we are thinking in these areas in the map and to where to measure. But the other ones that is we highlight in the document is this, and this is also the vision. In the vision, we need to offer information useful for the community who practice aquaculture, useful for the community that is with the fisheries working in the coastal area. And I like the word that Kim was talking about as suitable, appropriate, because in the past we tried to use the sentence for this area like unknown quality, because we can imagine an aquaculture, they really want to know that if the pH of the water is just about 8 units of pH or above, because it's the best quality that they need, or they need to stop to be pumping water when during upwelling with we have lower pH or undersaturated omega aragonites values below 1, okay, of course. And then it's different. They don't need the accuracy, the precision. They just need to take decisions. And we need, as a community, to offer an instrument, alert system, to tell them, to help them to take decisions. And then Kim, at the beginning, she was talking about how we need to learn and about to use this suitable and appropriate, because these two terms depend on which is the environment, which is the ecosystem, or which is the question particular that we need to apply this information. And then the talks from today will be talking about that, because as people who offer the funders, we can have some example of this. The GOA-ON on the box, many people are familiar with that, which consists of tools for the alkalinity, pH, and some supplies for, in the moment, they ship it about 70 kits, 16 countries. And as I mentioned, the last week, we have some meeting with the Latin American community, and the problem they have is how they can repair, how they can remain the instruments in good shape to be working. And the people that we have experience with the electrode, we know that a pH electrode for alkalinity, probably we know that in 6 months will be working, and this is the end. People who is getting this package, they brand new, they open, and they already have the problems because the sensors are not working. And then we have a lot of challenge for preparation, maybe the combination with the electronic engineers to be offered the support for the community, because we can give to be happy to get this gift, but we know that we'll be unhappy because we don't have the capability to repair or to keep in good shape the instruments. As a OARS in the outcome 3, we have that we know that we have some needs and challenges. Is the capability to monitoring, because the countries have diverse in the infrastructure. Also, it diverse the countries in the collaboration, because we know that we have some cultural restriction about the information. And we know that the people that we have sensors, we have some challenge to get theorems or secondary standards to calibration of the sensor. And then protocols, calibration, lack of fundings is something that we highlight in this document that you can see more details about that. Okay, and then finally, we can highlight these topics. We know that we need to monitoring the vulnerable areas with available and suitable sensors available to use for the community. We know that we need the appropriate sensor with the precision accuracy at the appropriate cost. And I mentioned the words suitable and appropriate depend on the question and with the area of with the particular application. And in the other challenge that we know is the availability of the commercial. It's really this kind of the problem that we have as an OA community. Okay, and then, well, my colleagues will be talking about these different topics. And just I want to final my time with you guys. Just that Vero and me, we will be very happy that we invite you to join us to engage and develop new projects and actions in these OARS. Thank you so much, and we hope you enjoy with the different talks. Thank you.
Thank you very much, team, for that great overview and the perspective of the OARS outcome number 3. Our next speaker is Adrian Sutton. Adrian's research focuses on advancing our understanding of the ocean carbon cycle and how it's changing over time. Her team maintains nearly 40 moored autonomous time series around the globe that track air-sea carbon dioxide exchange and ocean acidification. Adrian also collaborates with PMEL engineers on observing technology development, leading to the first autonomous circumnavigation of Antarctica in 2019 and the transfer of autonomous air-sea PCO2 observing technology to industry and non-profit partners. Prior to starting her career at PML, she spent 3 years at NOAA headquarters engaging the US Congress on issues concerning oceans and climate, which instilled her commitment to effective science communication that equips society to face the challenges associated with global change. So, Adrian, over to you.
Thank you, Kim, for that intro. Let's see. I'm going to share my entire screen here. So if I have tech issues at any point, please chime in and say something because I won't be able to see the chat. Yeah, great. Can someone just confirm they can see my slide?
Yes,
Great,
we can see that.
Yes, we can see it.
Awesome. Thank you. All right. So my talk today is meant for those who may have some familiarity with ocean acidification sensors, but are looking for advice and resources for choosing a sensor. So if you're a sensor expert in the audience, please chime in the discussion at the end if and, well, when I miss something. So yeah, looking for advice from others here too. Daria couldn't be here today, so I'll be presenting our combined material. And I'd also like to thank Yui and Taylor for contributing information to the presentation as well. So I will talk a bit about the different capabilities of sensors and what ocean carbon sensors are commercially available right now. I'll then present a framework for how to choose a sensor that best fits your specific needs. And I'll show some examples of research and development activities that are being done to test new sensors for various use cases. And then I will end with a list of resources that I share throughout the talk, so you can take a screenshot or a photo of those and take them along with you. Okay, so sensors have diverse characteristics and capabilities. So a sensor that is the most accurate may be larger and more complicated than a sensor with less accuracy. Some sensors are designed for integration with CTDs and other data systems and may not have their own data logging capability. Some have integrated anti-biofouling strategies and some don't. Some provide a true value of the parameter it's measuring, and other sensors may be precise but don't necessarily have the accuracy right out of the box. So you may be expected to do your own calibration or validation to determine that true value. Some sensors have drift that's well characterized and corrected internally before you even see a value. And some sensors have a drift that you need to characterize and correct for yourself, depending on the way that you're using that sensor. And if it's a sensor requiring you to calibrate it or correct for drift, then the data quality control process will require a bit more labor. So you have to really factor that into your decision on sensor choice as well. You may also find that some sensors already have a well-documented data QC process and associated software that may save you a lot of time, and some don't. Don't forget about refurbishment costs over the lifetime of the project as well. These costs may vary from a few hours of your time to clean and recalibrate the sensor yourself to up to several $1,000s of manufacturer's costs for refurbishment. So you need to take that into consideration. And if you need to have continuous measurements over a long period of time, but have a sensor that you have to send back to the manufacturer on a regular basis, then you really need more than just one sensor, right, to keep that, that unbroken observing record. And then finally, in looking at sensor spec sheets as you're doing research on different sensors, you may find something like an accuracy stated for one condition, like at 25 degrees C and a pH of 8 or something like that. And that's a sign that the sensor is well characterized in the lab at that one condition. But if you're planning to use it in the ocean with that has variability well beyond that one condition, you will likely need to do your own evaluation of sensor accuracy. And it's really important to dig through those sensor spec sheets and any peer-reviewed papers that evaluate the sensor and really talk to the authors to get their feedback on their experience with the sensors too. And, you know, in many cases, the sensor companies don't necessarily have the lab equipment or access to ocean observing platforms to do all of the tests that are really needed. So they rely on us, the science community, for those evaluations. So here is a table from what I think is the most recent sensor review paper from 2020. Some of these are designed to be deployed autonomously on ships, like the Hydrophia listed there. So you have to read the sensor specs and documentation carefully to understand the constraints of each sensors, like I talked about in that last slide. Since this was published, there have been some new sensors released. There's been some changes in availability and some changes in the sensor companies. So those are all shown in blue. I know a lot of people have CFETs and know about the issue with the couple-year hiatus in production of the Durafets that are used in those. But the good news is that the original manufacturer, Honeywell, is starting up production of those Durafets again. They do want to find another manufacturer of the chip that's used in those Durafets. So be aware that more modifications to the manufacturing process may be planned down the road. But overall, this is really positive news for this community. We also have good news in that a couple alkalinity sensors are now available. Because they are newer, we've had less field evaluations than some of the PCO2 and pH sensors that have been around for a while. So if you're interested in those, just be aware you may need to do some of your own testing under the specific conditions you'd like to use them in. And at the bottom, I'll provide these links again in the last slide where you can find more information about all of the sensors. There's one hardware directory managed by IOCCP that has links to, the manufacturer's website, spec sheets, sensor manuals, peer-reviewed, independent evaluation of the sensors. So that directory is really key. So once you understand what sensors are out there and where to find more information about them, it's really important to spend some time scoping out your specific needs and constraints before deciding on an observing design or methodology or sensor. This diagram is from the methodology document for the UN Sustainable Development Goal indicator for measuring ocean acidification. So I recommend taking a look at that document if you haven't already seen it. So first, you need to ask yourself what science questions you want to tackle using your observations. Are you interested in better understanding processes impacting local marine species and habitats? Where they are, that's going to impact where you implement the monitoring. Are you interested in tracking ocean acidification change over time? If so, you need to make sure that uncertainty in the measurements are sufficient for detecting that change over time that you want to detect. Or are you interested in how other stressors like eutrophication or hypoxia interact with ocean acidification? If so, you will need to consider, whether you need to add nutrients or oxygen to your sampling strategy. And, if you have a mandate or interest in providing specific information to stakeholders, then co-developing with them ahead of implementing a strategy is really important. So outlining those kind of questions and motivations at the beginning is really key. And then second, know your own capacity. And an ocean acidification observing strategy will be a balance of the research questions you've outlined and your constraints and opportunities. So those constraints may be the existing scientific and technical infrastructure at your lab, financial resources, not only to establish the observations, but to maintain them over time, and your accessibility to your monitoring sites. Like how many times can you go out to take validation samples or clean and swap out sensors? Another important capability that I've mentioned earlier is data management and quality control, which most of us tend to underestimate. So don't forget about considering the entire data processing workflow and the resources that you'll need for establishing that. And then last, in order to determine how often you need to sample, where you need to sample, and what measurement accuracy you need. It's really useful to have a sense for the natural variability in your region of interest and what forces are driving that variability, like tides, river runoff, upwelling, seasonal effects. If you're considering adding ocean acidification to a long-term water quality monitoring activity that's already being conducted, then those historical data sets can provide really important context for understanding that variability. You know, in cases where you have a salinity record, for example, a salinity-based proxy for total alkalinity can serve as your second carbon parameter and also help in your data QC and analysis. So doing some of that data synthesis work ahead of time can be really useful. And you may decide at the end of this process that you may not need high-frequency autonomous measurements, and that discrete sampling may be the best strategy for you. And that's okay, given, you know, sensor limitations and your project's constraints. You know, sensors are not always the answer. So choosing a fit-for-purpose sensor requires understanding different sensor capabilities and answering those 3 questions. So now I want to give a few examples of what testing and sensor evaluation looks like for one of the new pH sensors out on the market, which is a small optical sensor made by Pyroscience. So Pyroscience sells a standalone version of the sensor, and then also a version that with just the sensor that can be integrated into other types of data systems. And in this case, I'm showing here that the sensor company RBR is using it in their new temperature, oxygen, and pH sensor. And the BGC Argo community is just starting to integrate these into floats for testing as well. So given its small size and low power requirements, you know, that's why that community is pretty interested in it. And the company reports an accuracy of 0.05 for a very specific pH range. And so here's an example of some lab testing in comparison to discrete measurements of pH. And they're finding an accuracy in lab conditions over this range of pH that's much better after it's calibrated. So there's one example of a lab test that's really useful to find that accuracy over a larger range. Because these research groups are interested in using it on profiling platforms, they need to test for hysteresis. So in this case, Yui and Taylor and others identified the original foils used in this sensor didn't have a fast enough response time for that profiling application. So they tested faster response foils, and now the manufacturer is incorporating that option for a fast response version. So that's an example where, you know, researchers have done additional testing and have been able to improve the sensor. Daria and others also tested this for the Pico and also for their standalone sensor version, and found that response time varies depending on temperature, whether the sensor is ascending or descending, and whether you're looking at logarithmic pH values or hydrogen concentration values. pH response in these figures is shown on the left, and hydrogen ion concentration response on the right under the same scenarios, and their response looks different. Taylor and Yui have also been testing the drift rate. So the company reports a drift rate of greater than 0.005 per day at a pH of 8 and 25 degrees C. But really the user is on the hook to figure out whether that's consistent in the specific conditions they're working in that has more variability. So Taylor deployed a new Pico pH sensor next to a sensor that is well characterized and calibrated in situ. And they measured a drift rate for the Pico of about 0.001 pH per day in these summer and fall conditions typical of the coastal environment near their lab. And that's something they will have to account for in their post-processing of the data. So those were just some examples to provide a bit more insight into the type of testing that may be required for characterizing some of these sensors for specific use cases. Yeah, so just to wrap up, we've spent many years with access to PCO2 and pH sensors, but because those parameters co-vary, they are not the best pair for constraining the full ocean carbon system. So it's great to see that there are emerging options for alkalinity. They could end up being really useful for marine-based carbon dioxide removal approaches that aim to modify ocean alkalinity if the level of alkalinity modification is detectable by those sensors. So that'll be interesting to see. I get a lot of questions about what the best ocean carbon sensor is. And there is no best sensor for all research questions and all lab groups and all data needs. So you really have to answer those questions for yourself and research all the different sensor capabilities really to find that fit for purpose sensor that's really specific to your needs. And here's that list of resources that I promised that are the starting point for figuring that out, figuring out what sensor may best fit your needs. So please feel free to take a screenshot or a photo and take this information with you. And that's all I have. Thank you.
Thank you, Adrian. Thanks for that really useful overview of what's available on the market at the moment and what considerations you should have when you're choosing a sensor, and also for that summary slide that I hope people who are interested were able to take a photo of that if they want to pursue it. So if anyone's got questions for Adrian, we'll just wait to the end of the presentations and then we'll have an opportunity to answer for all of the speakers to answer some questions. So now we're going to move on to our next speaker, who is Kalina Grab. So Kalina Grab is one of the 3 GOA-ON secretariats and is a NAS Fellow in International Policy at the NIWA Ocean Acidification Program. Prior to this position, she earned a PhD in chemical oceanography from MIT Woods Hole Oceanographic Institution. She's passionate about applying science across sectors to make it actionable and accessible to global communities. In her free time, Kalina can be found studying the ocean dynamics through diving, surfing, sailing, and/or long swims on the beach. Kalina, over to you.
Thank you very much, Kim, for that. I will keep my video off for bandwidth, and I'm going to be talking about a different sensor than that which Adrian included in the overview. And as Kim mentioned, previously I completed my PhD in marine chemistry, and during this time I worked on a small handheld pH analyzer called the Fighter. And so today I'm going to share with you a little bit more about that. So imagine if communities around the world could have an instrument that they can hold in their hand and go out and collect pH data in order to contribute to decision-making, science, and education. So the Fighter can hopefully fulfill this vision. And so today I'm going to give you an overview of the instrument as well as an update from each of the different developers that are carrying it forward. So the Fighter developed developed first by William Pardis at Flathead Valley Community College about 6 he worked with to further the development. And since I joined the team to assist with some of the outreach and use of the fighter. And you can see here, we actually have presented to GOA-ON in the past in 2021. So you can look that up if you're interested in more details as well that I don't cover today. So the fighter has been rigorously tested and verified in cross-reference comparisons with benchtop spectrophotometers as well as reference materials. And there's a paper here that you can look up. And in that we have determined the accuracy of the fighter to 0.046. So for those of you that are very tuned in with pH instruments, this is within weather quality data for pH. And you might be wondering, well, what exactly is the fighter? So the fighter is a handheld, affordable, field durable instrument that is easy to use. And it's controlled through a smartphone app. So on the right of the screen is a screenshot of what the smartphone app looks like. And in the bottom left, you can see a picture of the fighter in my hand. And you'll notice that there is a sample cuvette area. So the way that the fighter works is it uses it's spec-based with indicator dye. And so you put a sample into the sample cuvette, put the stopper on it, measure the background on the app, open the stopper up, put some dye in it from the dye bottle, close the stopper, shake or turn the fighter up and down to mix the dye. And then on the app, you click measure pH. And then the app spits out to you, as you can see in there, a pH and a temperature and the salinity that you have entered. And so as I mentioned, this fighter has an accuracy that's comparable to other uncertainties associated with benchtop spectrophotometric measurements, such as dye impurities or cross inter-lab differences. And it's specifically designed for community-based science, and it can be used with minimal training. And so it's ideal for spatial and temporal sampling, and it can highlight small-scale variations around a large region. So the fighter has been tested in many different types of environments, and I'm going to show a few of those examples of how it's been used. On the left here, you can see some students that are on kayaks, and they were kayaking around and taking fighter samples. On the right is another image that shows fighter data collected around a peninsula. And this was also collected from a kayak, although different kayaks than are pictured on the left. And in this spatial survey, you can see that the pH differences were around 0.2 pH units. And so this was a large enough variation for the fighter to pick up on. The fighter was also tested against the ICME in a temporal deployment. So on the right, you can see the developer William Pardis deploying the ICME. And on the left is a graph where the y-axis is pH across the x-axis, which is time. And the black line is the ICME measurements. And the red dots are the time points when William took fighter measurements next to the ICME. And what you can see here is that the fighter was systematically slightly lower than the ICME, and this was by 0.003. So that's within the accuracy of the fighter as well. So the fighter has also been used for outreach and education, and a team at the National Marine Sanctuaries developed an ocean acidification plankton monitoring curriculum and pilot program. And this was adopted by the Ocean Guardian School, and it actually helped students at the Quileute Tribal School in La Push, Washington, earn an award from Nickelodeon called the Get Dirty Ambassadors Award. The fighter has also been used in a teaching element with Sea Education Association semester. And here I worked with students that used the fighter on kayaks, you can see in the picture on the left, and they spatially surveyed a mangrove system on the right. You can see those data. And these data show that there are variations within the mangrove system around 0.4 pH units. So again, within larger than the accuracy of the fighter. And with these students, I also conducted a survey to ask them about their experience in using the fighter. And what we found is that they said that the fighter motivated students to learn more about pH. They were also using the benchtop spec alongside the fighter, and they said that the fighter was easier to use. The students felt competent using the fighter on their own after a few minutes, and they also felt comfortable teaching their peers. And they also enjoyed using the fighter. So throughout the time that we have been working with the fighter, we have talked to many different interested partners. So those in community science, education and outreach, government agencies, international networks, local industries, and non-governmental organizations. And the thing that we have found is that there's no lack in interest in the fighter. The bigger hurdle that the collective team has come to is figuring out production mechanisms for the fighter and figuring out how to get in the hands of people that want it. And so in this position at OAP, we have begun checking in with the different avenues that are working on the fighter development to see what they have planned. And so today I'm going to share with you a little bit of an update from 3 different avenues that are still pursuing the development of the fighter and their visions for moving into the future. So first of all, Sunburst, they have received an SBIR, a small business innovative research grant from NIWA. And with this, they are in the second phase of this SBIR, and they have been facing difficulties with temperature variations between the sample water and the instrument. And they have worked to place a thermistor inside the cell so that they can accurately measure the temperature of the sample. And the graph on the right, you can see that they collected data from the fighter with the pH offset on the y-axis and temperature on the x-axis. And as the temperature is further to the right, it's closer to ambient conditions, and there is a smaller pH offset. So they found that if the sample temperature is close to the instrument temperature, then it's more accurate. And they tested this across different salinities, and they found similar conclusions for most salinities. They also tested the fighter against the YSI sonde, which is in the bottom right. And the blue dots are the YSI, where the orange is the spectrophotometer and the gray is the fighter. And so they found that the spectrophotometer and the fighter were systematically lower than the YSI, which was as to be expected due to the glass electrode in the YSI. And they did see that the fighter and the spec were comparable in measurements. So Sunburst is now working on a fighter 5.0, which they are planning to machine in pieces so they can be snapped together, and this can help increase their productivity for their production. And they also are focusing on the temperature measurements within the instrument. And they also hope to develop different fighter versions that can also measure total alkalinity, chlorophyll, and fluorescent dissolved organic matter as well. They're also looking into where to upload these data for end users to access it. And so if you have any interest in using these data and you have an opinion on what type of database you would like to see them in, feel free to reach out to myself or Sunburst as well. And so, as I mentioned, there's also other avenues outside of Sunburst that are still pursuing the fighter development. And one of those is David Long. He was the professor of the original developer, William Pardis, and he is at Cal Poly. And he's working at students, he's working with students for their own projects to develop the fighter further. And their vision is to separate the fighter into having a microprocessor and a sensor pod. And the sensor pod would be the innovative part that can keep changing with time. And the microsensor would be commercially available off the shelf, which could hopefully help with the longevity and the design, as well as accessibility and the production of the fighter. So there also is Jonathan Pfeiffer, who has worked with David Long in the past as well. And he currently is pursuing his PhD at Woods Hole Oceanographic Institution and MIT. And as his PhD project, he is creating a design that will be based on open source. And this he is calling the Phoenix. And the Phoenix will have design files and software code that is widely available and accessible. And this hopefully will help with the accessibility and production of the instrument. And he hopes to have a high enough accuracy to measure total alkalinity as well. So with that, the vision for the fighter still stands with, and all the different production and development avenues are hopefully moving towards a space where there could be fighters available for communities and indigenous nations so that they're able to engage and measure using the fighter to conduct science, make their own measurements, and use it for education. And this hopefully could increase OA monitoring and capacity and build international collaborations, and also enable countries to meet UN mandates to submit data to global pH databases. So with that, I'd like to acknowledge all the different people that have been involved in the fighter in the past. Like I mentioned, it is a large team that is involved in the fighter, and many of you on the call, I'm sure, have heard about the fighter. Maybe you have been beta testers for it as well. And I would just like to open up at the end for questions, and you can also feel free to reach out to myself or any other people mentioned that have been associated with the fighter if you have any questions, suggestions, thoughts, or ideas related to it. So with that, I would like to say thank you, and I will turn it back to Kim.
Thank you, Kalina. As Kalina said, if you've got any questions for her, then and for any of the other speakers, then in the session, then please either type them into the chat or hold them to the end of the 4 speakers, and we'll raise your hand and we'll have a short discussion session with about all of the different speakers at the end. So our next speaker is Dr. Dwight Gledhill. So Dwight serves as the acting director of the NIWA Ocean Acidification Program. He served with OAP since nearly the start of the program, and even worked towards the creation of a cross-agency initiative on ocean acidification in the years prior to the Federal Ocean Acidification Research and Monitoring Act. Since the program's inception, he's worked to ensure the program's research portfolio remains transdisciplinary, world-class, and responsive of the needs of NOAA's stakeholders. So, Dwight, the floor is yours.
Excellent. Thanks, Kim. Thanks, everyone. Let's see if I can get my presentation to work. Hopefully you can all see that. So, yeah, really enjoyed the earlier talks, and hopefully I can add a little something to the discussion. So we've been thinking a little bit at our program about exploring the options for open source approaches to tackling ocean acidification monitoring. So I'll just walk us through a few slides just to generate some conversation more than anything. So for those that aren't familiar with our program, the Ocean Acidification Program is really charged with evaluating and assessing the vulnerability of primarily U.S. Stakeholders to the potential effects of ocean acidification. So what does that mean? That means that we need to understand not only how the environment's changing, but how the biology is responding to those changes, and how the human communities that are dependent upon those species might be impacted. So clearly a major piece of the puzzle is describing the chemical environment that is changing due to acidification. So one of the key ways that our program does that is by sponsoring a whole suite of observations. Most of these, if not all of these, that our program currently sponsors are what the GOA-ON would refer to as climate quality. A major part of the superstructure that makes up the U.S. observing system on ocean acidification is utilizing the MAP CO2 system, which I think Adrienne spoke to in her previous talk. The MAP CO2 system, we have, I think she indicated there's about 40 that she's overseen, 40 to 50 of them around the world. About a baker's dozen, 13 or so, reside within the U.S. waters that our program oversees. The operational cost of these is considerable. They are, again, climate quality, but each individual node, depending on how you work the numbers, costs anywhere from $100,000 to $200,000 a year to maintain. So they're a hefty investment, but that's how you get climate quality monitoring. This network of fixed time series station is nested inside of a suite of surface and full water column ship-based observations. So we have fairly advanced technologies aboard a number of underway systems installed on vessels that transit throughout the U.S. large marine ecosystems. And those are supplemented every 4 or so years with a targeted biogeochemical campaign that involves not just biogeochemistry, but a whole litany of biological metrics as well. So those are all, that's a pretty robust climate quality observing system. But we do have challenges looking forward. This is, like I said, a very costly system. And our stakeholder base is increasingly asking us about dynamics in water masses that are very near shore, which is where their resources reside. So this is sort of that coastal acidification element where ocean acidification primary driver, or the driver of the carbonate system in those waters, the primary driver is not the uptake of anthropogenic CO2, although that can be a contributing element, but at least the short-term dynamics of it are controlled by the reactive processes occurring locally. So eutrophication, precipitation inputs into the system, local upwelling events, all of those are very dynamic and very complex, systems. So shown on the right is actually a product that we help sponsor out of VIMS, which shows this is actually a nowcast. So this is, I think, the forecast from yesterday, or the nowcast from yesterday, looking at the bottom saturation states for the Chesapeake Bay. And I've plotted on here our current climate quality observing station, the OA buoy, located in one spot. And so as you can see, while we get really good temporal resolution from the fixed time series stations, as Adrienne noted in her talk, it's important to very carefully think about the application of the data. And that's a very suitable application for tracking long-term acidification. But for many of the industries up in the Chesapeake Bay, they're encountering a much more dynamic system, both temporally and spatially. And because of that, we're unlikely in the short term ever going to be able to instrument ourselves out of that using climate quality observations. It's just too costly of an endeavor to do. So a few other low cost options were discussed in the previous talks. I'll talk a little bit about some options that might exist for open source technology. So what do we mean by open source technology? It means using off-the-shelf components in novel ways that you largely assemble yourself at your facility. You might use digital contract manufacturers. So you can go to websites now and actually provide them some design plans, and they might actually produce, a one-time discrete unit for you. A great example of this is actually the work that's being advanced right now at the Atlantic Oceanographic and Meteorological Laboratory in Miami by Ian Enoch's team. And there's a link here where you can go out to their advanced manufacturing and design laboratory, and they've got a whole suite of open source technologies that are available. One of which is actually a water sampler, which is pretty cool, which I'll talk about to some extent. It's open source. This is a SaaS system, so it's open source with respect to the physical design and the components and the electronic hardware and the software. You can go to that link right there right now, and you can actually download the build instructions and the part list. You can, if you happen to have access to a 3D printer, you can actually access the 3D printer files. All of the code can be pulled off, and it's completely open source. So it's really community based. So you can't buy this thing off the shelf, but you can potentially build it anywhere in the world. And the key benefit of this is it does help lower the bar for entry in some of the ocean observing applications. Clearly decreases the cost, at least of the instrument itself. Cuts out the cost of markup from the commercial production. Leverages community support technology enhancements and upgrades, so you can have an evolution of the technology by basically crowdsourcing the intellectual capabilities of the whole community. And it can increase information access for underserved communities. So those are all benefits to it. Some considerations for using open source technology, of course, is none of this so far that I've located is probably useful for climate quality, but there are a great many weather quality applications where it might be suitable. And we have to figure out a way to ensure that we have quality assurance built into the GOA-ON design. So if the GOA-ON community begins to adopt open source technologies, we probably need to be standing up some standardized community practices for how one would go about ensuring the data are intercomparable. While the uncertainties might be higher than they might be for climate, are those uncertainties carefully characterized and known? So that may be a more important consideration. This is there's a nice image here from the publication from Ian Enoch showing a pH test that was performed where he basically took these water samplers and he ran them in a controlled tank, and he can actually do direct measurements of the pH, and you could see how the sampled measurements were then analyzed later on actually performed relative to the direct measurements. So there's ways of actually quantifying the uncertainties of some of these approaches. You know, the nice thing about the sampler is that you can actually do a very high quality post-collection analysis of DIC, alkalinity, potentially spec pH, and that would give you triple constraint on the carbonate system. So you could examine things like organic alkalinity contributions. The nice things about them is the cost of the unit itself is somewhere below $500. So, you know, for the cost of one of the more advanced technology sensors, you might be able to get 50 of these things built. And so you could actually program them and set them out, and they can actually do a synoptic measurement at a given time, or you can actually set them out and have them trip in series so you can get a diurnal measurement. It wouldn't obviously be useful for long-term monitoring. You're not going to leave this thing out there more than probably a couple of weeks, I don't think, is the maximum deployment of them. Okay, so one of the challenges that Ian communicated to me with this open source technology has that the technical capacity needed to actually assemble them can sometimes be tricky. This might be tackled perhaps by means of like a training like we do with the GOA-ON kit in a box, or maybe we could meet with folks and actually walk them through their first build and train them. It does create a different approach to getting at measuring ocean acidification where it's not driven by profit, which, you know, that potentially could stall innovation. If specialized equipment and expertise are needed, it becomes less fitting for certain applications. All right, so some closing thoughts for our follow-up discussions. Other things we might think about. I don't know if there's any other key open source technologies available out there specific for carbonate chemistry. There may be analogs that we can look at other communities. So for example, the global monitoring networks for greenhouse gases for atmospheric CO2, they actually have a series of open source technologies that they're using, but I think it's relatively rare within ocean carbon chemistry to actually be using open source approaches. So maybe it's something we should think about. How can we ensure that we're coordinating any data that's being collected by open source technologies, coordinating it with climate quality reference networks for just so we can have some intercomparisons, ensure the data quality is at least understood if it's not clearly as good as climate quality would be. And what other risks and benefits am I missing? What am I not seeing here? So that's all I have. And I think with that, we can take questions, and I'll hand it off to Kim.
Thanks, Dwight, and thanks to all our speakers in this session. So now I'd like to open the floor to some questions for a couple of minutes. Katarina, have we had any questions through the chat?
Hey Kim, yeah, we've had a few questions to the chat, and I think some of the presenters have already started typing their answers into the Q&A box. So most of those are currently done. There's one open one from Kumiko, who said it would be great if we had some reliability indicators besides accuracy and precision. But other than that, if you have any more questions, you're also very welcome to use the raise hand button at the bottom of the control panel if you want to ask your question directly. Otherwise, please use the Q&A box.
Okay, then, while people are thinking about their questions and going through the answers, we've got some poll questions that we'd like you to be involved with. So we've got 5 questions, I think it is. So, Katharina, are you able to put up the slide with the link?
The sensor poll should be up now. All participants should be able to vote in that one. So you should be able to see a poll that has several questions on, starting with which of the carbon parameters do you measure with the deployed sensor? You can see some people have figured out how to vote. If you could all have a look at the poll, please, that would be very helpful.
So please, if you can take a minute or two to go through and answer those poll questions. The first couple are multi-choice, and then there's some others where you can enter some long-form answers. That would be just really useful for us to get an idea of who's doing what out there and what are the issues that you're facing in terms of having appropriate sensors that meet your needs, and what are the shortcomings that you see in the existing sensors that you have available to you. So I'll keep that poll open for a minute or two, and then we'll be able to check that and have a look at how people are filling in those polls. You can also look at the question and answers that people have contributed by looking at the question and answer in the Q&A portion at the bottom of your screen.
All right, so we'll go ahead and close the poll now. So looks like we got pretty good response. Thank you for participating. And here you can see I've shared the results on the screen. So the first one was, which carbon parameters do you measure? Looks like majority is pH, then PCO2 and DIC. Then what sensors do you currently use? So most is the CFET. And if you selected others, here's a few of the others. And then the next question is, are you happy with the performance? So 53% is no, and 47% is yes. And then what are the main shortcomings? So here, I'll just leave up a few of these so you can kind of glance through them to see what we're seeing. So CFET, currently unserviceable, failure rate too high, king time of PCO2, calibrations, sensors stopped working, no training, battery endurance, expensive cost and maintenance, long turnover for calibration that can't be done, calibration again, breakdowns and maintenance, troubleshooting, sensor malfunction, and reliability. And then what do you look for when purchasing a sensor. So stability, autonomous, ease of use, efficiency, durability, climate, weather, quality, precision, accuracy, cost, data quality, accuracy, fidelity, reliable parts, durability, precision, cost, efficiency, hardiness, and climate study accuracy. So I'm curious if, Kim, if you're online and you want to lead a discussion, if not, if any of the other speakers have comments to what they see here in these results.
Yeah, I would just, I'm trying to follow the Q&A and the poll at the same time, so it's a lot, but I'm not surprised by the answers. There's some comments in the chat and here in this poll that show sensor reliability is really important to people, and that's not something that is a topic you typically see in a spec sheet for a sensor. That's something that research groups kind of learn over time as they're using these sensors. So yeah, I could see the value in some kind of forum where the community can share that kind of information. But right now, that is a lot of information that is, held internally by groups that are working on these, and not necessarily doesn't end up in spec sheets or peer-reviewed pubs, but is important information. I agree.
Any other speakers have thoughts or reflections? I can also comment that, it sounds like, going back to what Adrian was saying, that it really depends on what your goal is for which sensor you use and what you're looking for. And I know that, when we think about what Adrian was speaking on versus what I presented on and what Dwight presented on, there's different approaches as to what types of sensors we have access to, which types of sensors we want to use, and what they're good for. So, speaking from my point of view with the fighter, that it doesn't necessarily address the shortcomings for everyone, and it's used only in a certain circumstance when you're looking for a more low cost sensor that is accessible, and that you want something on the order of weather quality data. So I think that, like Adrian said, some sort of forum to share these types of things or these insights would be really helpful in the community.
I would like just to add, related with the question from Kathleen Loader, because she's familiar with the instruments from alkalinity and pH. She asked for the expectations about manufacturers in terms of resource, which might be the expectations about the sensors, so the carbon chemistry community sensor we can use. I would like to think in the pH and alkalinity can be in the hands of our academic community to have progress and to learn to offer support. I don't see so far that any country can be able, working together with an electronic guy, to be able to create the electronic for a CFET the electronic for a spectrophotometric, as Kalina showed us, and to be able for any country to be able to develop their own instruments. This would be the idea. I can tell you that we used to, as a Mexico or Latin American countries, to buy in different companies, Seabird, all the communities, all the companies that you are familiar with, they are the source of the instrument for the current system. And it's expensive to buy the instrument, but it's also very expensive the support. Just to transport instrument from Argentina to US, from Mexico to US, it's very, very expensive. And then my ideal suggestion is that as a country, we need to be working in each country to be able to develop their own instruments to decrease the prices. This is what I guess. pH and alkalinity must be available. Can be possible. This is my suggestion about that. But really, this is my really strong suggestion about that. Maybe it's more very personal, but it's in the hands of everybody.
Yeah, I think you raise a good point, Martin. I think it's we have to realize that the sensor companies are not large. They're small. They're pretty small operations. So, you know, they can't do it all. However, they do need to hear feedback from users. So, you know, the one example that was given, if there are things in the manuals that are confusing, then I do think that users should reach out to the manufacturer about those things, because that's something that they can clarify and something that they, can improve for the community. If you're having issues with high failure rates, often technicians at the company can get on a phone call or a video call with you and, help you troubleshoot through those issues. So I think it's important feedback that they need to have, and they can help on some of those things. So yeah, contact them for sure. You're a customer.
All right, are there any last questions or thoughts to share? Okay, well, we would like to thank the organizers and moderators and speakers for such a great session. And thank you to the audience for joining us for OA Week 2023. Please do not forget to consult the website to register for any other sessions that may interest you. And if you would like to stay up to date with the GO-ON community, consider signing up as a GO-ON member if you're not one already. To discover more about ocean acidification research for sustainability, you can scan this QR code on the screen here or visit OARS-commitments.org. To discover, thank you. And we hope to see you at the next webinar, which happens tomorrow. Thank you, everyone.